For this video, I'm going to introduce you to matrices, which is the plural of matrix, and we're going to talk about some basic operations and what matrices are used for. So first, let's take a look at what matrices are. So a matrix is just a rectangular arrangement of data. The data is arranged in rows and columns. So rows are going to be the horizontal and columns are going to be the vertical. A matrix is usually described by its dimensions, which we're going to call order. So it's called the order of a matrix. And you say the number of rows, and then you say the number of columns. So it'll be something like 2 by 3 or 4 by 1. Each entry in the matrix is referenced by its location, and we'll talk about that. It's called an element. The location is given as a subscript listing of the rows and the columns, which will also take a look at what they're talking about there. But something like if the matrix was matrix A, then we would have element A1, 4. So row 1, column 4, and we'll get into that. So here's an example of a matrix. So this is matrix A. Again, the horizontal are the rows. So the top row, row 1, is the elements 1, 2, 3. Row 2 is elements 4, 5, and 6. And then you have columns that are the vertical. So 1 and 4 is in column 1. 2, 5 is in column 2. 3, 6 is in column 3. So each of those numbers is an element. Okay, so you've got all these different elements in here. This specific element right here is element A. So the matrix is capital letter A. And then when we do the element, we would do lowercase a. And then we do the row and then the column. So this element is in row 1, column 3. And so this is just the generic form. As you move up in math, when you're doing matrices, they'll call the rows I and the columns J. So I is going to be your row, J is your column number. So in this specific matrix, there are 2 rows and there are 3 columns. So then the order of this matrix is a 2 by 3. Oftentimes, in generic form, this is called M by N. So M being the number of rows, N being the number of columns, just in general. And then if we had a square matrix, that would mean that it's a 3 by 3 or a 4 by 4, 2 by 2, 6 by 6. So the rows and columns are exactly the same. So let's take a look at these examples. So I don't know why I have these in uppercase letters. So these should be A lowercase for the elements. Okay, so element 2, 3. So row 2. Okay, so we've got row 1 here, row 2 here, and then column 3. So column 1, 2, 3. So row 2, column 3 is element 6. So is the element 6. Row 2, column 1 is 4. Row 1, column 2. So row 1, column 2 is 2. 1, 1. So row 1, column 1 is 1. Row 1, column 3 is 3. Row 2, column 2 is 5. All right, then let's start taking a look at where matrices start to become useful. So when you're analyzing a lot of data, it'll just help you organize the data. So this table right here is carrying passengers as a risk factor, the number of deaths per 10 million trips. So based on the number of passengers and the age of the driver. So this says with 0 passengers, 16-year-olds get into have a risk factor of 2 accidents per 10 million trips, or 2 deaths per 10 million trips when they have 0 passengers, versus 17-year-olds have 1.5 deaths per 10 million trips, and 30 to 59-year-olds, that whole age group, okay, almost 30 years, is 0.7 deaths per 10 million trips. Okay, which if you get into insurance rates, that's why 16-year-olds and 17-year-olds have higher insurance rates, because their accidents are higher. So then when you get up to over 3 passengers, greater than or equal to 3 passengers, 16-year-olds, the risk factor, the number of deaths jumps up to 5.6. So it's almost triple, okay, when you end up with 3 passengers, almost triple the number of deaths in 10 million trips. So if we were going to create a matrix to represent this data, you would leave the information columns out. So you wouldn't write this or this. You would just be writing the numbers. Okay, so you just make a data table, and then we know that, like, we would know that we're looking at the different, you know, the top one is 0 passengers, 1, 2, 3, and if you're looking at multiple different age ranges. So then labeled that D, what are the dimensions of this matrix? Remember, the dimensions is rows by columns. So 1, 2, 3, 4 rows by 1, 2, 3 columns. So we're looking at 4 different passenger sizes, and then 3 different age ranges. So what do the rows represent? Number of passengers. And what do the columns represent? So different age groups. So we take a look at a couple more things. So identify the position of entry 3.8. So go over to your matrix and look at 3.8. So the position of it, so we're going to say D 1, 2, 3. So row 3. Column 1, 2. What value is identified as D4, 2? So row 4, so 1, 2, 3, 4, column 2, 1, 2. So row D4 is 4.5. And what does that value represent? So what does the 4.5 represent? So that is the number of deaths per 10 million for 17-year-olds with three or more. So I'm going to put greater than or equal to 3 passengers. Okay, so if a 17-year-old is driving with at least 3 passengers in their car, then there's 4.5 million, or there's 4.5 deaths per 10 million rides. Create a matrix that includes just teen drivers and label it T. So I've done that over here. So T for teen. So just 16-year-olds and 17-year-olds. So we would ignore this column and we would only use the first 2 columns. So this would be a matrix that represents that. So if we were just wanting to quickly compare teen drivers to each other. You can also use this a lot in statistics for sports. So this one is quarterback stats for the 2015 regular season and postseason. Okay, so regular season versus postseason. So create a matrix R to represent the data for the regular season. So again, we would just ignore now the names and then what the stats are and just fill in the data. So this is going to be a 1, 2, 3, 4 by 1, 2, 3, 4, 5. So we're comparing 4 quarterbacks and 5 different stats. So the rows are the quarterbacks and the columns are the different stats that we're comparing. And then do one for the postseason. So what are the dimensions of the matrix? So we just said that. So we're comparing 4 quarterbacks and 5 different stats. So 4 by 5. What is the value of R3, 4? So go to row 3, column 4. So 1, 2, 3, 1, 2, 3, 4. Okay, so it's 35. And what does it represent? So this is Palmer's touchdowns. Okay, so you can look here. So Palmer's touchdowns. So he had 35 touchdowns in the regular season. So Palmer threw 35 touchdowns in the regular season. That's what it represents. How about P34? So same quarterback, same column, okay, but this time it's in the postseason. So this one okay, or this element 3-4, P3-4 represents that Palmer threw 4 touchdowns in the postseason. So then if we took a look at now actually operating with these, so we've got the regular season matrix and we've got the postseason matrix. So what if we did a new matrix called T, and this matrix represented R plus P? Okay, so in order to do this, okay, remember that this represented, who was the first one? Newton. Okay, so Cam Newton, okay, and his attempts. Okay, so how many times did he throw the ball in the regular season? So Cam Newton threw 495 times in the regular season and 91 times in the postseason. Okay, so if you were trying to do R plus T, you want to be adding Cam Newton's regular season attempts and his postseason attempts together to get this new element here of 586. Okay, and then it would go to Cam Newton's next stat. So in the regular season, he had 296, completions, and then in the postseason he had 53. So then you're going to want to add those together to get 349. So it wouldn't make sense for you to go and add Cam Newton's attempts, okay, to Tom Brady's attempts in the postseason because they're not the same quarterback. So you want to be looking at their stats. So when you're going to add two matrices together, you need to add the corresponding elements, the ones that represent the same thing, okay, just regular season and postseason to get those added together. So then we would go on and do 3387, which I assume is total yards, okay, in the regular season and in the postseason. So add those together. So 3387 and 761 to get 4148. Next one would be 38, and then last one would be 12. When you add those corresponding elements together, and then you would do that for all 4 quarterbacks, right? So then you would go down to Brady and do 624 and 98 and get 722. So let's just do this first column here for everybody. So then we would do 537 and 81 and get 618, and then 469 and 68 to get 537. So you would go through it and add all the corresponding elements. So you would need to have matrices that are the exact same dimensions. So remember that the dimensions of this one was 4 by 5, and the dimensions here was 4 by 5. So then they were the exact same shape and the exact same size. So we would just add the corresponding elements to get that whole matrix filled in. And then this matrix is also going to be 4 by 5. So what does this represent? What's the T stand for? So total, the total stats for that player for the whole year. Because if they get to the postseason, then that counts for their total. So total, regular, and postseason. Okay, so total stats for 2015. All right. Oh, I never did a scalar multiplication one in here. Okay. So let me just do one more example here. Hang on one second. Okay, so I missed one on this screen back here to talk about scalar multiplication. So if we go back to the passengers in the car, so if I scroll down, so an insurance agency claims that when teens use seatbelts, the number of deaths per 10 million trips is reduced by 1/2. So reducing by 1/2 or 50%. Create a matrix that gives this data, label this N. Okay, so now we had the teen drivers here. So now we're going to take that matrix and we're going to say if they were to, that N represents them wearing a seatbelt. Okay, so now what's going to happen is it's going to cut the deaths in half. So we're just going to take each of these numbers and we're going to multiply by 1/2 or divide by 2. But dividing by 2 is the same as multiplying by 1/2. So 2 multiplied by 1/2 is 1. Half of 1.5 is 0.75. Half of 2.8 is 1.4. Half of 2.2 is 1.1. Half of 3.7 is 1.85. Half of 3.8 is 1.9. Half of 5.6 is 2.8. And then half of 4.5 is 2.25. So this is how you do scalar multiplication. So if you want, if all of your data is going to be doubled or tripled, or it's going to be half or 90% of, so you just take that scalar and you multiply it into all of the elements. Okay, don't skip any, because this insurance agency found, its underwriter or its adjuster found the, what is it called? It's actuary. Okay, so the insurance agency has an actuary that runs all this data and looks at all of the things and decides what the actual risk factor is. So when the teen driver was wearing a seatbelt, or when all of the drivers, when all the teens were wearing their seatbelt, then the risk factor is reduced by a half. So then you just take every element, reduce it by a half, multiply it into every element in there. So you're going to have the same order. So this one was a 4x2 matrix. So your answer matrix for this one, after you multiply the half in, stays the same size. So a recap on this was when you do matrix addition or subtraction, okay, as in with the quarterbacks, we added the regular season and the postseason together to get the total. You just add corresponding elements, okay, and if you're subtracting, same thing. Scalar multiplication, you just multiply whatever that constant, so scalar just stands for a constant number, so you just multiply that in to every element of the matrix. It's almost like distributing it in, so you just multiply it to everything. Don't skip anything, just get it in there to all of those.